Hey guys, welcome to join our talk. Today, we'll be demonstrating our engine, Quark. It is an obfuscation neglect Android malware scoring system. So my name is KunYu Chen. I'm a security researcher and a founder of Quark Engine. And we also have another speaker, JunWei. He's the co-founder of Quark Engine, and he gave talks in security conferences like HITB and DEF CON. So this is the outline. Number one, we will introduce our malware scoring system. And number two, we will show you how we design the Delphic bytecode loader. And number three, we will go through two cases of real malware analysis using Quark Engine. Number four, we will share our strategy of generating the detection rules. And the last thing, yes, the feature works. We still have a lot of things to do. All right, so let's introduce the malware scoring system. As we know, when developing a malware analysis engine, it is important to have a scoring system. However, those systems are either business secrets or too complicated. So therefore, we decided to create a simple but solid one and take that as a challenge. And since we wanted to design a novel scoring system, we stopped reading and decoding what other people do in the field of cybersecurity, because we don't want our ideas to be subjected to the existing systems. So we started to find ideas in fields other than cybersecurity, and luckily we found one. Yes, the best practice we found is the criminal law. So when sentenced the penalty for the criminal, the judge weights the penalties based on the criminal law. And after decoding the law, we find principles behind it. And we develop a scoring system for Android malware. There are only 8 principles decoded from the criminal law, and I'll go through it in the following slide. Now, let's see principle number 1. A malware crime consists of action and targets. In the criminal law, the definition of a crime consists of action and targets. For example, you steal money or kill people. So with this principle in mind, we developed this definition of a crime for Android malware. And the definition is the malware crime consists of action and targets. For example, steal photos or steal your banking account passwords. So now let's see principle number 2. We consider the loss of fame is greater than the loss of wealth. In the criminal law, physical body injury is more serious than psychological injury. So the principle we decoded here is when things are hard to recover, we consider it a felony. With this principle decoded, we develop our second principle. We consider the loss of fame is greater than the loss of wealth because it's easier to make money back than rebuild your reputation. Okay, now let's see principle number 3, arithmetic sequence. In the criminal law, when a murderer is sentenced 20 years in prison, and a robber is sentenced 7 years in prison for his crime. Why 20 and 7 years? Why the number? We found no obvious principles in the criminal law, so we use arithmetic sequence to weight the penalty of each crime. For example, the penalty weight of Y1 is 10, and Y2 is 20, Y3, 30, etc. So now let's see the most important part of the scoring system. We create an order theory, which consists of 3 principles. They are principle number 4, 5, and number 6. Let's first look at principle number 4. The later the stage, the more we are sure that the crime is practiced. As mentioned in chapter 4 of Taiwan criminal law, each crime consists of a sequence of behaviors. and those behaviors can be categorized in a specific order. So let's take murder for example. In stage 1, determined, it means somebody decided to kill someone. And in stage 2, conspiracy, it means he or she just started to make a plan for the murder. And in stage 3, preparation, it means buying stuff, for example, weapons, or arranging services for the murder plan. And in stage 4, start, it means when things are all set, the murderer takes action and is on the way to kill someone. And the last stage, stage 5, practice. It means the murderer does pull the trigger and shoots someone. So, as we can see here, the later the stage, the more we are sure that a crime is practiced. So with the principle in mind, we developed Android malware crime order theory. And in this theory, we also have 5 stages for the crime. For example, if a malware tries to send out your location data by using SMS, in stage 1, we will check if the related permission is requested by the malware. And then we will check if the key native API is called. And number 3, in stage 3, we will see if certain combination of native API exist. And then we will check if the APIs are called in a specific order. And finally, we check if the APIs are handling the same register. Okay, so now you can see from this picture, this is a two-dimensional map for Android malware crime. And for the crimes, we put them in y-axis. And for each crime, we use x-axis to see the evidence we caught for the crime. So x5, y1 means in crime number 1, we have found native APIs that are called in the correct sequence and they're handling the same register. And x3, y5 means in crime number 5, we have found a certain combination of native APIs that is used in this APK. So now let's look at principle number 5. The more evidence we caught, the more penalty weight we give. So we give stage 2 more weights than stage 1 and stage 3 more weights than stage 2, etc. Okay, principle number 6, proportional sequence. As we decode it from the criminal law, the later the stage, the more we're sure that a crime is practiced. So we consider proportional sequence, for example, 2 to the power of n, to present such principle in our scoring system. All right, principle number 7. Crimes are independent events. So for simplicity, we assume crimes are independent events and penalty weights can be added up directly. So this is an example of adding up 2 crimes. In a malware, we find 2 crimes. They're stealing photos and stealing your banking account password. So the calculation of a total penalty weight is quite simple. For each crime, we use penalty weight of crime to multiply proportion of caught evidence and add up the result of the 2. The last principle, principle number 8, threshold generate system. After calculating the total penalty weight of for the crime, for the malware, we need to have threat level threshold so that we can tell which threat level does the malware fit in. Unfortunately, we can't find them. We can't find them in the criminal law, but we know we need to design a threshold generate system for that, not just give any number by intuition. So we decide that threshold for each level is the sum of the same proportion of caught evidence multiplies penalty weights of crimes. Yeah, we know it's not a perfect one, but we're sure that we build a foundation for future optimization. All right, now let's talk about the design logic of Dalvik bytecode loader and JunWei. He will take care of this part.
Hi everyone, my name is JunWei, and I will take care of this part. Our Delphi bytecode loader is actually the implementation of the Android malware crime order theory. We implement every stage of the theory. There are 5 stages. The first 3 stages are easy. We simply use APIs in another open source tool, Android Guard, to implement the first 3 stages. As I just mentioned, the implementation of the first 3 stages are easy, but in stage 4, we need to do a little bit more. So before the implementation, we need to know what does stage 4 do. In stage 4, we find the calling sequence of native APIs and check if they are called in a specific order. For example, if a malware sends out your location data by SNS, then first it will call native API getCellLocation to get your location data, and then call native API sendTextMessage to send your location data by SNS. Normally, native APIs are work-in functions. So we trace back to see which function is cross-referenced from the native APIs. And we call those functions the parent function. And we will keep tracing back until we find the mutual parent function for both the native APIs. Here is the example. sendTextMessage is called by sendSNS, which is the parent function of sendTextMessage, and getCellLocation is called by getLocation, which is the parent function of getCellLocation. And if we keep tracing back, we will see that both sendSNS and getLocation shares the same parent function, sendMessage. And after we find the mutual parent function, we will scan through a small line code of the mutual parent function and check which function is called first. So this is the small line code of sendMessage. We can see that getLocation is called first to get location data of the cell phone. And the sendSNS is called to send out the location data. And in stage 4, we found out that our design can also overcome the obfuscation techniques used by the malware. When applying obfuscation techniques, functions except native APIs are renamed. This has made the decompiled source code hard to read for humans. But machine can still run the code because the logic of the code remains the same. Here is the example. When applying obfuscation techniques, native API sendTextMessage is called by function K, and function K is called by function F. The other native API, getCellLocation, is called by function E. And both function E and F shares the same parent function, A. You see, if you start reading the decompiled source code of A, it will be hard to figure out what is going on there. And by the way, since our goal is to find the mutual parent function, so it doesn't matter how many layers the wrappers are. Now, let's see the implementation of stage 5. Yes, this is the most important part. In stage 5, we need to confirm that if the native APIs are handling the same register. Let's use the send example. Send out your location data by using SNS. So when native API get cell location is called, it will return the location data of the cell phone. And what we do in stage 5 is to check if the other native API send text message sends out the location data returned from get cell location. So in stage 5, we simulate the CPU operation. We read line by line of the small elite source code and operate like CPUs to get two things. First, the value of every register. Second, the information like functions who have operated the same register. To make this happen, we create a self-defined data type. We call it register object. In each register object, we store three kinds of information. Number one, the register name. Number two, the value of the register. Number three, the function who use this register. Let's see the example. So the register name is V7, and the value of the register is the string. And the string appends the value of string 1 and the result of function 1. And then we can see that the register is used as the input resource of the function 2. By the way, when filling the value of used by which function in a register object, we expand every register by cross-referencing other register object in the table. So, for example, by cross-referencing, we know that V8 is a string called user location, and V3 is a function called getLocation. As you can see in the lower right corner, the result of getLocation is append to the string user location, and the new string is sent out by using function send_as. In other words, the value of register V7 is generated by using function getLocation, which has native API 1 in it, and the value is used as the input for function send_as, which has native API 2 in it. So now we prove that by using the register objects, we can check if the APIs are handling the same register. So after we scan through the source code, we produce lots of register objects. And those register objects will be organized with a two-dimensional Python list. It is a similar idea like hash table. We use it to boost out the read and write of the list. So now, let's see the table. As you can see here, register V4 has 3 register objects. That means in the source code we scanned, V4 was used 3 times. And every time when it was used, we store the present value of the register and the function who used it if there's one. So basically, the whole table is the history of the registers. So when we finish constructing the table, we then scan through all register objects in the table to check if the native APIs are handling the same register. So now, let's see how to use Quark engine to analyze the malware. Now, let's get back to KunYu.
Hi, it's me again. So in this section, we prepare 2 malware. One is non-obfuscated, and the other one is obfuscated. And for each malware, we will show how we detect the behavior of the malware with the detection rule. Now let's look at the first malware, This is a non-obfuscated one. And we will use the rule in Quark engine to detect whether if the malware sends out cell phone location data by using SMS. So this is the detailed report of Quark engine. In this report, the engine shows the detection results of one single malware behavior, or you can say one single malware crime. So for example, we try to find if the malware sent out your location data by using SMS. In this report, we list out the evidence we found in each stage of the Android malware crime author theory. And this report shows we find evidence in every stage, which means we have 100% of confidence that the malware has this behavior. So let's see. In stage 1, permissions like send SMS, access course locations, and find locations are requested. In the second stage, key native APIs like get cell locations and send text messages are used. And in stage 3, we find certain combinations of native API exist. And in stage 4, we found out that functions like send message and do byte, the APIs are called in the right sequence. And in stage 5, in function send message, we found out that those APIs are handling the send register. So now let's think. If you're analyzing this malware and you want to trace the compiled source code to see the evidence, how do you do it? Our suggestion is you start reading the report backwards. That means you start from stage 5. For example, in stage 5, we know that inside the function of send message, it has two functions that contains the two native API respectively, and they're handling the same register. So you start to locate function send message in the decompiled source code. And in stage 4, we know that those two functions are called in the right sequence. So we can start to find functions that contains the native APIs and check if they are really called in the right sequence. The information of the two functions and the sequence will be shown in the next version of Quark engine. And recently, we have developed a new feature, a call graph for high potential malicious activity. I call it the Google map for malware analysis. Now let's see. On top of the graph, we start our journey from the mutual parent function. And then, according to the map, we can see it clearly that which function wrapped the native APIs and the calling sequence of these functions. Wow, this is amazing, isn't it? So now let's start the journey. We start from send message, the mutual parent function of the key native APIs. And we can see in this map, it first called function get location, and then it calls function send SMS. And in function get location, it calls native API get cell location. So let's see the other wrapped function send SMS. In this function, it calls native API send text message. Now we have the roadmap, and let's read the source code. Let's locate function send message, and we found out two functions that contains the two native APIs respectively. Your send SMS and get location. And if we dive into the source code of function get location, we will see that it contains native API get cell location. And if we dive in the source code of function send SMS, we will see that it contains native API send text message. So the code here means it first collects your cell phone location data and send it out through SMS. So now let's dive into the source code of function get location. As you can see in the source code, it tries to call native API, get cell location, and return this information at the end of the code. And now let's dive into the source code of function send SMS. Native API send text message is used to send out the location information. It's quite simple, isn't it? Now let's look at the second malware. This is an obfuscated one. We will use the rule in Quark engine to find whether if the malware detect Wi-Fi hotspot by gathering information like active network info and cell phone location. Okay, so as a malware analyst, we read the report backwards. As you can see, in stage 5, there are functions like p.a, @view.c, and af.run. And those functions has two functions that contains the native APIs respectively, and they're handling the same register. And in stage 4, these two functions are also called in the right sequence in function p.a, @view.c, and af.run. So according to the reports, we can say that the malware has the behavior of Wi-Fi hotspot detection in 3 parts of the source code. And we can pick any part for further analysis. So we pick function p.a. So again, let's start a journey. Let's choose parent function p.a. As we can see in the map, it first calls function ap.a, and then it calls function f.f. And in the function ap.a, it calls native API get active network info. And let's look at another wrapped function, f.f. In this function, it calls native API get cell location. So now we know the roadmap to trace the code. Okay, so let's locate function p.a. And we found out that 2 functions that contains the 2 native APIs respectively. There are ap.a and f.f. And if we dive into the source code of function of ap.a, we will see that it contains native API get active network info. And if we dive into the source code of function f.f, we will see that it contains native API get cell location. So the code here means after collecting information from function ap.a and f.f, they send the information as an input for function am.a. So now let's dive into the source code of function ap.a. As you can see in the source code, it tries to call native API, get active network info, and return the related information at some points. And now let's dive into the source code of f.f. Native API get cell location is used to get the cell phone location data. And this information is processed with some other strings. At the end of this function, it returns the string with information. As mentioned earlier, after collecting information from function ap.a and f.f, they use the information as an input for function am.a. And we notice one thing, that function am.a used byte rate output string as one of its input parameter. And we know when saying byte rate output string, it means the function is probably trying to write the data into the file. This is amazing, isn't it? So with Quark engine, malware analysts can really boost up their productivity. Okay, so now I will introduce our detection rule generate strategy. So why do we need to develop the detection rule generate strategy? Because to make our engine practical and easy to use, we need to have more detection rules. However, the speed of rule generated by human is quite slow. And human generated rule is subjected to his or her experiences of malware analysis. So we developed a rule generate strategy to boost up the production of detection rules. Since our goal is to find all kinds of behavior in the malware, so if we use permissions and native APIs to generate all possible rules, we will have an amazing amount of rules. After generating the rules, we then use Quark engine to find the intersection between those amazing amounts of rules and the malware we prepared. In other words, we find rules that matched the malware behaviors. However, this is not a good way to generate detection rules because it's time and resource consuming. So we develop a 7-step rule generate strategy. Step 1, we crawl down all native API information on Android official API reference. For example, this is the native API information of send text message. You can see the input parameters, return values, and the description of this API. Okay, step 2, we did a little bit modification to our engine. We ignore the permission checks in stage 1 of the Android malware crime author theory. And in step 3, we find all kinds of API combination and generate rules without permission information. And in step 4, we use the modified Quark engine to find the intersection of the rules and the malwares. We call rules in the intersection the first stage verified rules. In other words, these rules need to be verified again. And since we don't need to generate rules with permissions and verify the permissions in Quark engine, the whole process of rule production speeds up. In stage 5, we try to generate rules with permissions. Inside the intersection, we have first stage verified rules matched with the malwares. We then use the first stage rules and permissions in the matched malware to generate rules with permission, which is the second stage rules. In step 6, we then use Quark engine, the full function version of Quark engine, to find again the intersection of the second stage rules, which are the one with the permission and malware we prepared. After that, for each rules, we label the number of matched malware. For example, the behavior of rule number 1 can be found in 100 malware. In step 7, after labeling the rules, we then sort the rules by number of matched malware. We will review the rules from the highest matched one. All right, the last part, future works. As I mentioned earlier, we still have a lot of things to do. For example, we need to have more detection rules, and we also need to deal with .so files and pack the APKs. And we want to have more features of Delvik bytecode loader, for example, the downloader. And applying the scoring system to other binary formats is also in our to-do list. And we noticed that API changes in different versions of Android. We will also take care of this part in the next version of Quark engine. Oh, and we probably would change the core library since Android God is quite inactive recently. And one more thing I would like to say. Actually, we make Quark itself easier to be integrated to other tools. For example, users now can import Quark as a Python library and output the analysis result as a JSON file. Also, Quark is collected in Black Arc Linux and is integrated to a threat intelligence analysis tool, Intel-O. You can just install them and give it a shot. And there is one nugget I would like to share here. We work at the limit of our tools. When new tools come along, new things are possible. Okay, that's all for today. And if you have any question, please feel free to DM our Twitter accounts. Thank you.